I'm showing Greg Rosendig in this video.
Ah, nice. Okay. Here, grab my hands. You gotta help me sit down. Oh, both. Oh, slowly! God, that hurt.
You filmed that.
It was gravity.
Don't worry.
Oh, yeah, easy for. Ow.
Your weight was distributed across all the knees.
I say that. Okay, where's that block? Okay.
Right here?
Oh, yeah, right here. Beautiful. It's like trying to talk with an elephant in your chest. Okay, go in. Okay, just saying. So you want to hit right in the middle.
Okay.
Okay, now do like a good half to 3/4 swing.
Okay.
Does that make sense?
Yes.
Because if you don't hit it hard enough, that's actually worse. Because if you don't hit it hard enough, it doesn't break. And then all that energy goes into my chest.
Yeah.
Oh, no, I want it
It's
to
supposed to
shatter.
absorb all.
Shattering is better than not breaking at all. Okay? So you're going to hit now. Hand me that. Safety first. Yeah, I'm worried about safety as I lay on a bed of nails with a sledgehammer. Okay, so get right in the middle.
I do not want to be known as the kid who sent Bertie to the hospital.
Been doing this for decades. I've been hurt, but not gone to the hospital. Okay, you ready? That was a good one. Yeah,
I think I'm about as scared as you.
no, I'm good. Okay, all right.
And we'll
Give
be
him a
right back
second.
for a commercial.
Okay. All right, just a second here, Jackson.
Jackson, that's not going to stay.
Yeah, I know.
Because Caleb and I are looking around the video and I want the one of them.
Okay. Oh. All right.
Oh, got a couple holes.
Okay.
Just those
All right. So, one time, I only did this once. So I did this like at a grade school, and I had a white shirt on, and I had a jacket on. But before I put on the jacket, I took a red marker and put little red dots across my back. Oh. And so when I stood up, I had my back to them, and I took the jacket off. And they're going, oh! It's like, no, it's just a joke. They never invited me back. I don't know, weird, oddly enough. So,
Stinky legs.
no, I'm more of a two-step kind of guy. All right, so we survived. Now, would I have done this if there were only, like, say, 10 nails?
No.
What? Same action?
Less surface area to absorb all your body weight.
Well, it's more of a distribution.
Right.
Okay? So this is about 100 pounds of nails. So by having my weight distributed, it still hurts. Trust me, you lay down, it hurts. But that weight is distributed over the whole thing. Now, what if we had done that and we had just put an apple underneath the block? Wouldn't work. Why?
Because it doesn't have as much mass.
Yeah, so the apple would accelerate and we would have driven the apple into the bed of nails. So, but because I have enough mass and that weight is distributed, I just got a few like pin marks in my back. Okay, here we go.
Some good acupuncture.
Say hi. Say hi.
In 10 years from now, if it was me, that sledgehammer would not have gone to the wrong place. I'm not strong enough to, yeah.
Do we still need this?
Huh?
'Cause I don't know if it's going to stay.
That's close enough. We're about done.
Hey, Birkin. What? You have to get your tetanus shot.
Why does everyone hate me today?
It's just a flash line. Okay.
You got that for me while you're done.
So, again, quick refresher. Are you going to answer anything on this sheet of paper?
No.
Absolutely not. So, let me get you through one of these so that you don't flip out and end up in the fetal position sucking your thumb. So, if you look at number 6, it says If with no friction, the force F results in acceleration A when acting on mass M, then tripling the mass and increasing the force sixfold will result in an acceleration of, okay. And you read that, you think, what is going on here? So I'm going to show you two ways that you can do this. Oddly enough, they both start with the idea that force equals mass times acceleration. Basic idea, okay? Now, if you were a numbers kind of person, what's an easy numeric value I could use for force? 1 Newton. What's an easy value for mass? So therefore, an easy acceleration would be 1. And that's how 1 Newton is defined, is the force needed to take a 1 kilogram mass and make it accelerate at 1 meter per second squared. That's how that's defined. So now we're going to change it. So you're told that we're going to triple the mass. So instead of 1 kilogram, what are you going to have? 3 kilograms, because it gets tripled, right? Okay. Then you're told that we're going to increase the force 6-fold. So instead of 1 N, you're going to have 6 N. So therefore, to make everything balance, what has to happen to your acceleration?
2.
So it doubles, okay? So this is the smash mouth physics way. You put in numbers, you see what happens. The elegant mathematical way to do this is just start with F equals ma. Now, you're going to triple the mass. So instead of m, what are you going to have?
3m.
3m. You're going to increase the force 6-fold. So instead of F, you're going to have 6F. Then to make it balance, you have to have 2A. Okay? There you go. So when you get down to problem number 1, okay, this does not have to be on graph paper, but it does kind of need to be to scale. So you've got the masses, and you're going to compute the weights of these masses. When I ask you to calculate weight, what am I asking you to determine? Newtons, gravitational force. Do not make these negative, just get the numbers. So obviously 1 kilogram is going to weigh 9.8 newtons, okay? Just G times, mass times G. So you're going to put mass on the x-axis, weight on the y-axis. Just keep everything positive. Don't make it weird. Just have positive mass and positive force. You're going to find the slope of the line. When you get to number 4, let me kind of give you a visual of what's happening on number 4. You're going to have a 500-gram mass, and you're going to put it on a scale that measures in newtons. Okay? It's 500-gram mass. What does a 500-gram mass weigh? That's its mass. What does a 500-gram mass weigh? 4.9. If you take 0.5 times 9.8, you get 4.9. So there's a downward pull of 4.90 newtons. There's your FG. If you want to make that negative, I would. Now, what's the scale doing? Pushing back up with the value, with how much force? 4.9 newtons. So there's your normal force, 4.90 newtons. Everything would add up to 0. Now, I'm going to take a balloon and I'm going to attach that to it. Okay? It's a hydrogen or helium-filled balloon. That's going to provide a little bit of upward force. Okay? Not a lot, but a little. So then I tell you, once you attach the scale, or once you attach the balloon, the reading on the scale drops to 4.80 newtons. So how much upward force was provided by the balloon? 0.1. Do not make this 0.1, because what does everything still have to add up to? Keep that in mind. When you get to number 5 on the back side, so let me kind of give you this visual. You've got a 4.8 kilogram box that you're pushing at a constant velocity. So what do all the forces add up to? 0. What's the only reason you have to keep applying a force to the box?
It's accelerating.
No, because it's not accelerating.
It has a velocity, a positive.
What are you pushing? You're pushing it. What are you overcoming?
Friction.
Friction. So whatever force you have to apply is balancing out the frictional mafia going in the opposite direction, right? So if you can figure out what the frictional mafia is, you know how hard you have to push. So I've given you the coefficient of friction as 0.38. So I've given you mu. If you know mu and you know the mass of the box, which you know, what can you find?
Friction.
Force friction. Now, so visualize this. Here's the block. You're pushing it. And then you go, I'm tired. And you just stop pushing it. As soon as you stop pushing it, what's the block going to begin to do? Slow down, because at that point, your forces are not in equilibrium. You have an unbalanced force. Because what did you lose? Which force did you lose when you stopped pushing? Force applied. So the frictional mafia basically goes, Big Tony goes, you're not going to pay us? You're not going to be in business, okay? So basically the frictional mafia shuts you down. Are you going to accelerate once you stop pushing it?
Yeah.
But that acceleration is going to make you slow down. So your velocity time graph is a horizontal line because you're pushing it at constant velocity time graph. As soon as you stop pushing it, what's your velocity time graph going to do?
Drop to 0.
Drop to 0. Keep that in mind. Number 6 is the easiest problem on the entire assignment. Do not make number 6 difficult. It is the easiest problem on the entire assignment. You have a mass and you have an acceleration. How are you going to calculate force? F equals ma. That's all you have to do. Now, 7, 8, and 9 all require the use of F equals ma, but you have to calculate the accelerations. So let me give you kind of a visual on number 9. So this guy falls out of the plane. Luckily, he lands in a pile of snow. So he's traveling when he hits the snow at 53.6 meters per second, which is, they think is about 120 miles per hour. So he was going 53.6 meters per second when he hits the snow. What's his final velocity going to be at the bottom of the crater? 0. You're also going to know a distance, which is 1.07 meters. So you're going to know an initial velocity, 53.6. What's his final velocity?
0.
You know a distance. You need to find an acceleration. What are you going to use? That equation. Right? Use that equation. Okay, I'm done. You're on your own. I'm going to go take some ibuprofen. No, I really am. So, okay.